now let's look at some examples where we're rotating around lines that are not the x and y axes. So define R as the region bounded above by the graph of f of x equals x squared and below by the x-axis over the interval 0 to 1. Find the volume of the solid of revolution formed by revolving R around the line x equals -2. Okay, so as always, we need to start with a graph in order to see what the region looks like that we're actually trying to rotate. So let's see, I think I'll draw like this. F of x equals x squared is of course just a parabola centered at the origin. So I'll just kind of draw it like that. Probably only need one side of it, that's all right. We're bounded below by the x-axis, so that's there. And we're on the interval from 0 to 1, so let's just say this is 1 right here. All right, so there's my region. And you know what, I think I'll go ahead and erase this side because we don't really need that. We're rotating now around the line x equals -2. So here's -1, -2. So this is my axis of rotation now. And we'll see what that changes. Okay, so of course we will need to decide if we want to use horizontal or vertical rectangles. Now this is an example you probably could use either, but I tend to use a vertical rectangle unless there's a very good reason not to. So this vertical rectangle would be parallel to the axis of rotation, which would invoke the shell method. All right, so that volume then is going to be the integral from the start to the end of my interval. And I'm going to need the length of each shell multiplied by the height of each shell. And I've just decided to integrate a vertical rectangle, so that's dx. Okay, so the integral from a to b, well, our rectangles start here from x equals 0 and then go over to x equals 1, so that's pretty straightforward. The length of each shell. All right, so what happens here is we really need to see how far away each rectangle is from the axis at any point in time. So as this rectangle moves, the distance from as it moves from 0 to 1, the distance of that rectangle from the axis of rotation changes. Now normally we just use x, but we can't just use the position x here because we would need to be rotating around the y-axis. What we're going to do is we're going to measure this distance just using, linear distance, just horizontal, vertical, linear distance here. And we need to take the most positive point here, which is going to be whatever the x value is of this rectangle, and subtract the most negative point, which is the constant -2. So this radius, so this is like a radius function here, because as I rotate this rectangle around this axis, it's forming a circle, and each circle has a radius. So the radius of this circle is x minus -2, which is of course x plus 2. So this is the distance of this rectangle from the axis of rotation at any point in time. So if that's the radius function, then we can convert that into the length by making it a circumference, because the circumference of the circle formed is the length of the shell, and that is done by just multiplying the radius by 2 pi. So 2 pi times x plus 2, and then we multiply by the height of the rectangle, and height always comes from the height of the function in this case, so just f of x, and in this situation it is x squared, and then we would integrate dx. Alright, so simplifying some things here, I'll pull out the 2 pi, and I could distribute x squared into these parentheses and get rid of those parentheses and say this is x cubed plus 2x squared dx. Now the actual integration I'll just leave up to the function f(int) in the calculator. So let's see what we get. Integrating from 0 up to 1, x cubed plus 2x squared dx. And changing that into a fraction, we get 11/12. So 2 pi times 11/12. 2 goes into the 12 6 times, so that leaves me 11 pi over 6 as the volume of this region when it's rotated around this axis. In our next example, we want to find the volume of the solid generated by rotating the region bounded by the x-axis and the function x equals y minus y squared around the line y equals 2. Okay, so let's first take a look at what this region looks like. And this time, our functions are functions of y, which we're not maybe quite as familiar with. And as I've mentioned before, you can use your calculator to help you graph those. You just need to change the mode of your calculator to parametric form. And then when you go under y equals, you can change x and functions for y directly. Y is our independent variable here, so I'll just leave it as t. And then x is going to be whatever I'm saying y is minus y squared. So just substituting in t for those. And let me check the window. That looks fine. All right, so it's a parabola, which is not too big of a surprise because this is a squared function, but it's pointing to the opening to the left here. And it looks like it has zeros at 0 and 1, although they're fairly small to see there. You might want to zoom in to verify, but I think that's pretty well understandable there. So let's graph this. All right, so we had intersections at 0 and 1, and the graph basically looked something like this right here. Okay, it doesn't really matter, I think, how far this goes in beyond here. We could probably calculate it if we wanted to, but I think it's fine not knowing. Then we are rotating around the line y equals 2. Well, I didn't really give myself enough space for that. Let me use some magic here and make some space. There we go. All right, so this needs to go up to 2, and I'll just make that the 2. That's fine. All right, so y equals 2 is my axis of rotation. Rotating around there. The region here, it was actually stated, it's bounded by the x-axis in this function, so that is a mistake, and that should have been the y-axis. So let me fix that. There we go. All right, now there's my region that I'm looking for. and I want to rotate this around the line y equals 2. So I can now choose if I want to use a vertical or a horizontal rectangle. A vertical rectangle would make me do some work here in changing this function especially into something that's y in terms of x, which is going to be really difficult to do. So I think we probably need to use a horizontal rectangle here. So we'll be integrating dy, but also that means our rectangle is parallel to the axis of rotation, so we would be using the shell method. So volume is found by doing the integral from a to b of the length of each shell times the height of each shell, and we've determined we're going to integrate dy. Okay, so the endpoints of integration, remember this variable is y, so that means the endpoints are functions of y, so I'm going from y equals 0 to y equals 1. And that's our endpoints of integration. The length here is going to be the circumference of a circle formed by rotating this rectangle around the y-axis. So I need to figure out what this distance is right here. And we're thinking of it as a radius. We just want to ensure it's positive, so we're going to take the most positive part, which is always the constant 2, minus the location of this rectangle, which is always the coordinate y, and 2 minus y would always result in a positive number, making the radius positive, and thus making the circumference of the circle positive. So the circumference then is 2 pi times my radius function. The height of each rectangle is just defined by the function itself. So this distance right here is just the function, although I wrote y and I wrote x and it's a function of y. And that's just going to be y minus y squared dy. I'll take out the 2 pi and let fn int calculate this integral for me. So let's see, going from 0 to 1, and I've got 2 minus, I'm still in the parametric mode, so the variable for parametric equations is t. It's okay that you don't use x or y here, you can use any variable. I'll just use the t, that's fine. T minus t squared. I just have to make sure I integrate dt in the end so that I'm integrating with respect to the correct variable. It looks like I might be missing a set of parentheses. Let me go back in here and add one more. That closes that parentheses. We should be good. All right, so 0.25, which is just 1/4. I don't need the calculator to help me change that into a fraction. 2 goes into 4 twice, so this becomes pi over 2. And there we have it.